Okay, let's begin. So, what we're going to do, what we're doing is, we're going to go through the examples that I wrote down on the board last class. I will give you guys some tips, general facts you might want to know whenever the excuse arises, I suppose. So let's actually go into the first one. So A. So it's example 1, part A. We're to compute this guy. Example 1, part B. Supposed to compute this guy.
I'm not too sure about how
C. I want to compute this guy. Okay, so how do we want to do this one? Yeah?
we solve for the integral and then plug it into.
Okay, so what is that here?
1/3 x cubed.
Right, add 1 to the power, divide by the new power. And this is a notation, I don't believe I've introduced this before, but you'd write a vertical bar here and write the numbers on that bar. So that's just a notational thing. So if you want to write, say, f of b minus f of a, that's the same as writing f of x with a vertical bar beside it. It's just a notation, I think. So I can write this notation. And what that means is I'm going to take the top number, plug into the function, and evaluate it. Then I'm going to put a minus sign and take the bottom number, plug into the function, and evaluate it. This is the part 1 of the first, the fundamental theorem of calculus, part 1. So I'm going to take the 1, plug it in. Minus, I'm going to take the 0, plug it in. And of course the answer here is 1/3, which we actually computed this the long way using a limit of a Riemann sum. So basically what that 1/3 is, the interpretation of that 1/3 is that if you have the graph y equals x squared, so I'm going to ask you what is the area under that graph between 0 and 1? The answer would be 1/3. This one, of course, is very similar. This would be the antiderivative, which we know the power rule for integrals right now. With those numbers, you will actually plug in 1 minus, you plug in a minus 1. That will become 1/3 plus 1/3. You actually get 2/3. What you can realize this is of course, if someone were to ask you, what is the area under that graph between -1 and 1? And your answer would be 2/3. Now, at this point, I want to mention something that's going to be convenient for you to know in helpful fact. It's going to be quite helpful for you in this calc class and future calc classes, is that something like this always happens with even functions. So you might remember that x squared is an even function. We looked at even functions very briefly a long time ago. Those were the guys that the negative x values. So if you have a y value for one x value, it's negative. Will actually give you the same y value. So that is f is even. That means f of negative x equals f of x. Also means it's symmetric about the y-axis, and it turns out for all such functions, if you integrate from minus a to a of that function, it will always be the double from 0 to a. because all the rectangles you constructed here, there will be an equivalent rectangle constructed over there. And so the areas of both sides will be the same. And so you pretty much only have to worry about half the work and double it. Being able to plug in 0 as opposed to a negative constant can make your life a lot easier. This is always true for even functions. Okay? This isn't true in general, this is true for even functions. And the interval minus a to a, this is a separate thing. The interval minus a to a is called a balanced interval. So you'll see that phrase, you'll hear that phrase all the time. It's called a balanced interval because you're kind of balanced around 0. Right? The distance you are to the right of 0 is the same as the distance you are from the left of 0. So this interval is called balanced. So we can say if you integrate an even function on a balanced interval, it's just double the integral and half the integral. Right? So you can say the statement that way. Right? So this is something you can know in general, and it will be quite helpful to you in general in Calc 2 and beyond. So it's no coincidence that this is 2/3 and that was 1/3. In other words, that's what I'm trying to say. This is a general fact with even functions. Now, let's move on. Let's look at this guy. So what's the antiderivative of cosine? Yeah?
Negative sign.
No, that's the derivative of cosine. Be careful.
Is it just sign?
It's sine. Right? Because if I differentiate positive sine of x, I get positive cosine. Right? So be careful. The sine and cosine, the signs actually flip when you go from a derivative rule to an integral rule. So be careful of that. The derivative of cosine is negative sine, but the antiderivative of cosine is positive sine. So you do that. Now, what we will do is plug in sine of pi over 2. Of course, this is minus sine of 0. You remember sine of 0 is 0. What's sine of pi over 2?
One.
No, it's 1. So here, what this is, if you look at the graph of cosine, looks like that, where this stops at 2 pi. Pi over 2 is where it hits 0 the first time for the cosine. And what you just computed was that area. That area happens to be 1. Now to our next example. D. Integral from 0 to 2 pi sine of x. Integral from 0 to pi over 3 of 3 cosine squared x. Okay, so this one, antiderivative of sine of x. What is that? Yeah, you guys can just say it, you don't have to.
Negative cosine.
Huh? So that's going to be what?
Negative cosine.
Negative cosine. So kind of the opposite intuition of your derivative. So you have to watch out for that. Very common mistake to mix up the signs when dealing with sine and cosine antiderivatives versus derivatives. And so if you differentiate cosine, you would get a negative sign. The negative times the negative makes it positive. Now you can do that. Here we have cosine of 2 pi minus cosine of 0. What's cosine of 2 pi?
1.
It's 1. So you have a minus 1. Here, what's cosine of 0?
1.
It's also 1. So I have a minus 1, a negative 1. This gives us a plus 1, which gives you 0 as the answer. And you might wonder, well, why? How is that? Well, for this one, there's another thing I want to tell you about later. For this one, you'd realize what that actually means is, this is the reason why I kept saying that integral was the area under f, and I often put under in quotations, because what actually happened here was the following. So here we're looking at the sine function. And what you'll notice is the area between 0 and pi will give us some value. Now it turns out that the area between pi and 2 pi is also going to give us a value, but it turns out that it will give us the negative value. Right? So sometimes our integrals can give us what we call a negative area. It doesn't mean that the area is actually negative, it's based on the way that we actually set up what an integral means. Right? So you recall that how we defined the integral was we put rectangles, right? And then we added up the areas of those rectangles. And how did we compute the areas of those rectangles? Well, it was the height of the rectangle, which is given by the y value, times the width of the rectangle, which was delta x. Now if you apply that same principle to a part of a curve that is below, you would of course have rectangles going down and touching the function and coming up. And now applying that same formula, what you'll realize is that if the height of the rectangle is given by the y value, this y value is now going to be negative. And so if you multiply it by your delta x, it turns out that when your curve is underneath the x-axis, the integral is going to give you a negative area because it's taking all negative y values. So that's something you'd have to look out for. We'll talk more about that next time. But in this case, what ends up happening here, why you get the answer of 0, is it turns out that the sine is a very regular function. The area here is actually exactly equal to the area there, and so they kind of cancel each other out. So the integral will actually tell us this area minus that area, which cancels out and gives you 0. So it's not that the area, the actual area bounded by the curve is not 0, it's just that it has positive and negative components that kind of cancel each other out. Something you'd have to look out for. This also gives me an excuse to talk about another general fact that you want to know. So that's a very important geometrical interpretation. In terms of sine and cosine specifically though, here's another very helpful fact. So I'll give you some basic ones first. Turns out that if you integrate sine or cosine over like 0 to 2 pi, I'm stating this one specifically because it happens to show up pretty often, the answer is going to be 0. And this can be something that you just know now. You don't waste time actually computing it. In fact, you can actually generalize this even more. You can say that if you want to integrate a sine or a cosine over any interval whose length is a multiple of the period of sine and cosine, you will always actually get 0. Because something like this will always happen. The parts on top will be equivalent to the parts on the bottom. So once you move through a full 2 pi window, no matter where it's shifted, or any multiple of that window, no matter where it's shifted, the positives and the negatives are going to cancel each other out. So starting at any point and moving to that point plus or minus 2k pi is actually going to give you 0 for the sine or cosine. Right? Where k is any integral, you will automatically get 0. So if I'm integrating from 7 pi to 9 pi, it's 0. Or if I'm integrating from 0 to 4 pi, it's also 0. Right? The positives and the negatives are going to cancel out. You can even generalize this even a little bit more to say something like, if you have sine of x, n times x, where n is a constant, right? So you can imagine you're integrating sine of 2x, sine of 7x, sine of 3x, sine of a half x. Turns out the period of that function will be 2 pi divided by k, and so this will be 2k pi over n. And and integrating on any such interval will give you 0. So that's just a pro tip. So I am also teaching a multivariable calc course this semester, and you'd be surprised how often we end up in a situation similar to this. So we'll be computing some crazy integral or something, and we end up in a situation where it's like, okay, we need to integrate between 0 and 2 pi of like a sine cubed function and a cosine cubed function, and then it's minus sine of 2 this plus, you know, cosine squared this d theta, right? Or something similar, any weird thing like that. And it turns out that technically, without the limits here, if you want to figure out the antiderivatives of these guys, I'm going to actually show you how to compute the antiderivative of something like this. The first step would be to do something like, think of this as sine squared theta times sine theta, and think of this as cosine squared theta times cosine theta. And you do something called a substitution, which we're going to talk about in a few lectures. However, just knowing that there's a sine and a cosine component, the way it's going to work out with the substitution is, because you're over 0 to 2 pi, these guys are actually going to give you 0. So you end up with a problem like this, and you can immediately just ignore these parts. They're going to contribute 0. Similarly, the sine of 2 pi, its period is pi. You're literally integrating over a multiple of its period. That part is also going to give you 0. For this part, you'll actually use the double angle formula. You write this as 1/2 plus 1/2 cosine 2 theta, and that part is going to go to 0. So you'll end up in a problem where you have to compute this, but really, it's that, right? And students who don't know any better are going to spend a long time doing that when really they should just be doing this. Right, so knowing little tricks like these whenever you're in a situation where you're going to be dealing with trig functions a lot, which happens a lot in calculus 2 and multi, little tricks like these can really save you a lot of time. Right, and whenever you're doing over a definite integral, you're going over a multiple of the period of sine or cosine, it allows you to ignore a lot of things. And really, a huge integral problem can be a small one if you know how to look at it correctly. So that's just another helpful fact that I have excuse to mention here. Let's go to another example. How'd you do that one? Yeah?
You could pull out a 3 and 5, it's a constant, and you have 1 over cosine squared x, you can treat it as secant squared x.
Right. Or we can just do that right away. This is just 3 secant squared x dx. Okay? So you'd simplify it, you'd rewrite it into something more familiar. What you definitely don't want to do is try to apply your antiderivative rules in the top and the bottom separately, because that doesn't work. Something like that doesn't even work for derivatives, right? That's why we have a quotient rule and we have a product rule. Antiderivatives are in general much more difficult to compute than derivatives, and so if something is not going to work for a derivative, it's not going to work for an antiderivative in general. So if you can't just apply a derivative rule to the top and bottom of a fraction, you're not going to be able to do it with an integral rule. So at very least, you should know that that's not an option. But we do know that simplifying before taking a derivative is often a nice thing to do, and so it turns out it's also a nice thing to do with antiderivatives. So you see something strange, like a division or a product, probably the first thing you want to think of is, how can I simplify the thing I want to find the antiderivative of? And in this case, it simplifies to 3 secant squared. What's the antiderivative of secant squared? Tangent. If I differentiate tangent, I get secant squared. So this is 3 tangent pi over 3 minus 3 tangent of 0. We know that's 0. What's tangent of pi over 3? radical 3. So remember, here what you'd think of is tangent is just sine over cosine. So I want to think about what is sine of pi over 3 divided by cosine of pi over 3. Now if you remember that table, 1, 2, 3, 3, 2, 1, you know that the pi over 3 is over here. So the sine is going to give you radical 3 over 2, the cosine is going to give you 1 over 2. So you take radical 3 over 2 divided by 1 over 2, you get radical 3. What about this one? Yeah?
You change sine squared x into 1 minus cosine squared x.
Right, same principle here. Now I didn't tell you how to integrate something like sine 2x yet, even though I kind of told you you really apply the half angle formula if you had to. But here you don't have to, because sine squared plus cosine squared is 1. So you can literally just replace that with 1. Antiderivative of 1 is of course x. So you'll end up with 13 minus 0. 13 would be the answer here. Find the antiderivative from 1 to 4 of x minus 3 over the square root of x. And how do you do that? Some ideas what would be sure. Ideas?
Could you make the round x in the denominator equal to x negative 1/2 and then distribute that into x minus 3 top?
Yeah. I'd do pretty much the same thing I would do if I wanted to take the derivative of this. I'd simplify it first. Because I wouldn't do the quotient rule and something like that, because there's only one thing in the denominator. So chances are it would be overkill. Divide radical x into each of the top terms. You'll end up with x to the 1/2 minus 3 x to the minus 1/2. Now you apply your rules. What would be the antiderivative of x to the 1/2? Or would you differentiate to get radical x?
2/3 x to the 3/2.
2/3 x to the 3/2 by the power rule, right? Add 1 to the power, you get 3/2. Divide by the new power. Divided by 3/2 is the same as multiplying by 2/3. Same thing here. Add 1 to the power, you get x to the 1/2. Divide by 1/2, it's the same as multiplying by 2. So you end up with 6 here, the 2 times the 3, and plug in 1 and 4. Now, the first one you plug in is the 4 on top. That's what the fundamental theorem of calculus tells us we need to do. here's something we never had to do in all these examples yet. Parentheses here, very important, because it has to be distributed. So whenever you're subtracting, you need to put those guys in parentheses. So I would put the 1 in here. I would just get 2/3 minus plugging in 1 here gives me 6. So ultimately, this gives me well, what's 4 to the 3 halves?
16 over 3.
Well, 4 to the 3 halves is 8.
Yeah.
Right? Because you square root the 4, then you cube it, you get 8 times 2, you get 16. So that's 16 over 3. 4 to the 1 half is 2. 6 times, well, 2. Here, this will be minus 2/3. And here, this will be plus 6. Here, at 16/3 minus 2/3, that's 14/3. Here, I have 6 minus 2 times 6, so that's just minus 6. And 6 is 18 over 3, minus 4 over 3. What does it mean to have a minus answer? Well, it means on this interval, the part of the function that's underneath the x-axis has a greater area than the part that's above. That's why you have a negative answer here. So you get like a negative area, it's a net area under the function. What about this one? Distribute the x. Squared minus 2x, the antiderivative of that, and for x squared. So there it comes x cubed over 3. 2x becomes what? X squared. Comes in 4. Plug in the 4. 4 cubed over 3 minus 4 squared minus 4 0. 4, 16 times 4, that's 64 over 3 minus 16 over 3. Well, not 16 over 3. It's 4 squared is 16, but I multiply it and divide it by 3, so that's 3 times 16. Well, my 64 is actually going to be 4 times 16. So I have 4 16s minus 3 16s, I only have 1 16. This one. Not terribly crazy. Easy application of the power rule. Add 1 to the power, divide by the new power. Plug in a 1, minus plug in a negative 1. Turns out here, you also get 0. Now I have an excuse to talk about another helpful fact. See, x cubed is our quintessential example of an odd function. Helpful fact. I forgot what number we're at. I think it's number 3. Now, suppose f is odd, meaning f of minus x is the negative of f of x on a balanced interval. So if you want to integrate an odd function on a balanced interval, then it turns out it will always be the case that an odd function will give you 0 area on a balanced interval. And why is that? Well, because we know how odd functions behave. Given some random x value here, we'll get some random y value. But if we take the negative of that x value, we get exactly the negative of that y value, which means the area under the curve over here is going to be exactly the negative of the area under the curve over there, because we have equivalent rectangles being erected, but they're pretty much opposite orientation. You always have the positive part killing the negative part. And so an integral of an odd function over a balanced interval is always 0. And it turns out that that is also pretty helpful. There are going to be times in Calc 2 and beyond where you end up with really crazy integrals. something like this. Right? And they'll say, oh, somehow you get this has to be integrated from -4 to 4 for whatever reason. And you might think, oh, I should just apply some antiderivative rule and do what I've always been doing. Turns out this particular function has no antiderivative. There's no function you can come up with that when you differentiate, you get that. However, it's easy to see that this is an odd function, because if I replace all x's with negative x's, I will get the negative of the function. So I know that this would be 0, no calculations necessary. So I think situations like that come up all the time as well. So you see x cubed integrated between -1 and 1. You'll notice that x cubed is an odd function. You could immediately here say, oh, this is 0 because odd function on balance interval. Such functions always integrate to 0. Let's go to the second set of examples, where we want to get used to applying the second part of the fundamental theorem of calculus. So here, this example is to just find the derivative of the given function. And A here was given g of x is equal to the integral 1 to x is sine. You need to find its derivative. B. And this is also something that we have happening quite often. Get a function that's defined in terms of an integral. But we still want to be able to do calculus with such a function. And what does the second fundamental theorem of calculus say the derivative of that such a thing would look like?
It would be f of x, so it would be sine or square root of x squared plus 3.
That's the answer. Second fundamental theorem of calculus. Pretty much a direct application. If you're integrating from a constant up to x of some function, you want to find the derivative of that, it's just plug the x into the function. Okay. What about this one? Now, one thing you want to do is, again, you want to be careful with your rules. You want to memorize them, which I'm not sure you guys have memorized the rules yet for this segment. Start memorizing your antiderivative rules, memorize the fundamental theorem of calculus. Once you do that, you, of course, realize here that there's something off with this when it comes to the rule. See, the second fundamental theorem of calculus speaks about differentiating something that looks like this, and the answer is f of x. Well, the fact that the constant is on the bottom and the x is on top should not be considered a trivial matter. Here, of course, you have the opposite. So, let me tell you how to deal with that situation. And we can actually use the first fundamental theorem of calculus to figure out how to deal with that situation. One of many ways. You can also use an area interpretation, but it turns out, also an important property I would say that you should know. If you're integrating any function from a to b, f of x dx, it turns out that you can switch the limits of the integral. Put the b down here, the a up here. Not without consequence though. You need to put a negative sign in front. There are a couple ways you can see this. One, you can take the area interpretation. Of course, if I go from a to b, and what I can do is I can put up all these rectangles going above. The idea is if I reflect the function over the x-axis, now the rectangles would all be negative. And I'll get the negative area. So this guy is what's going to happen there. If I kind of flip the world upside down, that's what will happen. Another way to see this is that by the first fundamental theorem of calculus, this is going to be big F of B minus big F of A, which it turns out is the negative of big F of A minus big F of B, which again by the first fundamental theorem of calculus is going to be what we get when we put B down here and A up there. So, with that notion, it turns out that this is actually easily dealt with just by putting a negative sign in front. And so our derivative, now applying the second fundamental theorem of calculus, is just going to be the negative of cosine x plus 2. So another important idea, we can swap the limits on an integral by just taking a negative sign in front. This follows from the first fundamental theorem of calculus that we are allowed to do that. I mean, there are other ways to see it, but not, when we have the fundamental theorem of calculus, there are a lot of things that we can get for free without a lot of work. We don't have to worry about, oh, what would the rectangles look like, or how is the area kind of working here? I don't care. If fundamental theorem of calculus is true, we can actually manipulate that expression to figure out a lot of really cool stuff. C. Find f prime. Ideas here. Yeah?
Just be f prime of x equals cube root of 2 plus x to the 6th. Is that just wrong?
No. Well, why? The rule doesn't have x cubed in it, does it?
Yes, you can just cube the x.
Cube the x.
Yeah. When you do the whole thing, it's
Is that what your intuition from derivatives would tell you to do? Because we want to do derivatives, right? If I have a basic rule that I can state in terms of x pretty easily. Say I want to differentiate x cubed. That's 3x squared. This is the rule with x. What if I replace that x with something else? Say x squared plus 1 all cubed. How does the derivative change? Oh, it doesn't change, I just do the same thing. would that be? How do you deal with this situation? You need the chain rule. Right? Because it's not just x. We're finding a derivative here. The same would apply. The second fundamental theorem of calculus gives you a rule that has x in it. It means if that x is replaced by any other function, the chain rule will kick in. So it's not just that you plug in that x cubed, you have to now multiply by its derivative. So that's another rule. We can generalize the second fundamental theorem of calculus using the chain rule. In other words, if I want to find the derivative of an integral that goes from some constant up to some function, right? So it's not just x. Then that's going to be differentiate as you normally would, just by taking that guy and plugging in here. But then you have to multiply by the derivative of the inside function. So that rule would apply here. Right? You need the chain rule. We're differentiating, and we have a rule that tells us how to deal with it. If there's an x on top, if you replace that x with any other function, you can deal with it easily by just applying the chain rule. So what we're going to do is we're going to start out by doing what you're saying, but we're not going to be done at that point. We need to actually multiply by its derivative. So we have to multiply this by 3x squared in order to be complete. So that would be 3x squared times the cube root of 2 plus x to the 6th. That would be the derivative. Because the chain rule takes effect. So I guess that can be helpful fact number 4. And we have one more example, which is going to give me an excuse to give you another helpful fact. Helpful fact number 5. The goal here is to find the derivative of this guy, which of course should present some obvious challenges here. I don't remember if I...
It was like this one.
Now here we're in a special situation. First of all, we don't just have x's on the interval. Second of all, we don't have any constants on the interval. Now that is an issue because we need a constant on the interval to apply this rule. So now the question would be, would we be able to apply this rule if I have one function up here and another function down there that's not a constant? Well, this leads us to helpful fact number 5. Where I should start this. Helpful fact number 5. And this is it's kind of like a property of integrals that we can know now. We can break up integrals. We can break up integrals. Over subintervals. Now, intuitively, in the area interpretation, that makes sense because if I have some function where I'm finding the area under that function between a and b, of course I should get the exact same answer if I pick a random point c, find the area up to that point, and then add that to the area up to the rest, right? Add the area in 2 parts. There's nothing wrong with that. In fact, I can do this for any finite number of slices I can make. and I can just add up the areas. This would tell me that the area from A to B of a function, I can think of it as, well, find the area from A up to C of the function, and add that to the area from C up to B of the function. I can break up an integral over subintervals. So if there's one big interval I care about, I can actually do that integral over subintervals of that interval, and just add them all up, and I'll obtain the same result. I can obtain the area in pieces. Another way you can see this, of course, is if you look at A to C f dx plus C to B of f dx. Fundamental theorem of calculus says this is going to be big F of C minus big F of A plus big F of B minus big F of C. Of course, positive F of C cancels minus F of C. You're going to end up with F of B minus F of A, which is, of course, you know, the integral from A to B. So the fundamental theorem of calculus gives you a nice non-geometric proof here. But whatever the case is, it turns out that I can actually break up an interval into more convenient subintervals. That being said, because I know I need a constant here, and at this point, this makes you think that the C has to be in between A and B, but it doesn't. You can see that this will work for any random number I put in. I can just throw it in there whenever it's convenient, and it will work out by the fundamental theorem of calculus. So this basically tells me I can actually just split this integral into two parts. I can go from x squared plus 1 up to some constant c. I don't even particularly care what that constant looks like at the moment. And then add that c going up to the x cubed. Now, we already know how to deal with this situation. It's just a matter of the chain rule. And we already know how to deal with this situation, actually. You do two of the tricks that I told you. First, you flip it so that the second fundamental theorem of calculus applies. Then, because you have an x squared plus 1 instead of an x, you need the chain rule. So I first flip that by putting the negative sign. And now I can just find the derivative. This means that our p prime is going to look like, I'm going to plug this in and multiply by its derivative. Plus, I'm going to plug this in and multiply by its derivative. And so that would be the answer. You can simplify this a little bit. Cancel that into that, and whatever. It's 3x cubed over x minus this thing. That will be your derivative. So, lots of examples there. Practice that, practice even more in your textbook. Computing antiderivatives and finding derivatives in this situation is something you'd be expected to do relatively quickly. On the next test and the final, there will be one problem where I'll actually just punch out 5 of these parts A through E. I'll just be able to just get through them quickly. That's going to be one problem. Yeah.
Is this the stuff that's going to be on the quiz tomorrow?
The quiz tomorrow goes up to part 1 of the fundamental theorem of calculus, because I actually mentioned that last week. So up to the first set of examples that I gave. So be able to the first half of the class. Okay. See you guys tomorrow.